The oldest light we can see is still arriving here. It comes from the very beginning of the observable universe. It's like a fossil. It carries the original pattern for everything. This faint glow tells the whole story of where we came from and where we're going. It holds hidden information about the universe's birth, its explosive start, and the invisible structure of everything. What is our most basic link to the cosmos? That light came from a world completely different from ours. To get it, you have to go back to a time before stars, before planets, before anything we'd call a place. After the universe started, it wasn't clear. It was a hot, dense fog for hundreds of thousands of years. A plasma, particles so thick light couldn't go far. It would just scatter, get absorbed, get sent out again. It was a glowing, opaque soup, and the light was stuck inside it. That was the cosmic dark age, though it wasn't dark in terms of heat. It was a uniform, brilliant glow, but trapped. Then things changed. The universe kept expanding and cooling, and when it cooled past a certain point, something happened. The free electrons and protons in that plasma finally slowed down. They combined. They made the first atoms, neutral hydrogen, and right then the fog lifted. The universe became transparent for the first time, and all that light that had been bouncing around, trapped for eons, was suddenly free. It burst out, in every direction, one final, brilliant flash. That event is called recombination. That flash is the first light that could ever really travel. And we're still catching that light now. It's been stretched by the expansion of space. Over billions of years, cooled, shifted from visible light down to a faint microwave hum. What we call the cosmic microwave background. It's not a picture of the very first instant. It's a baby picture of the universe when it was about 380,000 years old. It's the afterglow of that release, a snapshot of the infant cosmos, and in it there's a frozen imprint of every ripple, every density variation, the ones that would later seed the galaxies. So what caused that escape? And what's locked inside that first photograph of everything? That first free light, it fills everything now, the whole cosmos. We call it the cosmic microwave background, but that name, it doesn't really capture it. It's not just a glow, it's a thermal echo, almost perfect. A snapshot of the universe from one precise moment in its infancy, and it carries a temperature. After traveling for over 13 billion years, that temperature has been stretched, cooled down, to just 2.7 degrees above absolute zero. That's the chill of deep space. A cold so deep it sets the baseline for everything. What's startling is how uniform it is. You look in any direction, this ancient light, it paints the sky the same. A near identical hue. A smooth canvas of microwaves. The most uniform thing we've ever seen. That sameness tells us the early universe was in a state of near-perfect thermal equilibrium. A hot, dense soup. Conditions were virtually the same everywhere, but that perfection in the cosmos, it's often a mask for something deeper. Because within that smooth canvas, you find the most crucial details. Tiny fluctuations, almost imperceptible, minute variations in temperature. Just millionths of a degree warmer or cooler from one patch of sky to the next. These anisotropies, they're the universe's first fingerprints. They're not random noise. They're the magnified imprints of quantum fluctuations. Microscopic ripples in reality, stretched to cosmic proportions during the universe's first explosive growth spurt. Inflation. Those tiny wrinkles in space-time, they became the seeds of all structure. The slightly denser patches where the light is a tiny bit cooler, they had more gravitational pull. Over eons, they drew in more matter. The slightly warmer, less dense patches became the great voids. From these microscopic imperfections grew everything. Every galaxy, every cluster, every filament in the cosmic web. So this light, it's far more than a relic. It's a detailed map. A map of the universe's initial conditions. A direct line of sight to its formative moments, written in a language of subtle temperature differences. To read this map, to decipher that ancient message, we needed to build eyes sensitive enough to see its faint, cold whisper across the gulf of time and space. We first heard this ancient whisper almost by accident. For a long time, it was just a theory. Then, in the 1960s, two radio astronomers, Arno, Penzias, and Wilson, were using a big horn antenna in New Jersey. They were trying to map radio waves from the galaxy, but they kept hearing this hiss. It was everywhere all the time. They checked everything. They even cleaned out pigeons from the antenna, thinking that was the problem, but the noise stayed. It was a mystery, until they talked to some theorists at Princeton who had been working on what the early universe's afterglow should look like. And that hiss was it. That was the echo. They found it without even looking for it, and they got the Nobel Prize for it. That first detection was like hearing a single, faint note. But to understand the music, we needed better ears. We had to build more sensitive observatories. The first big one was the COBE satellite, launched in '89. From space, it confirmed the signal had the perfect spectrum of ancient heat. And it made the first map, a blurry one, of the tiny temperature variations. It saw the universe's first fingerprints, the seeds for everything. Then came WMAP in 2001. That was like putting on glasses. Where COBE map was blurry, WMAP was sharp. It measured the fluctuations so well it could tell us the age of the universe, its makeup, its shape. The most precise one so far is the Planck satellite. It operated 1 million miles from Earth, cooled almost to absolute zero. Its job was to filter out the noise. The modern universe is loud. Our own galaxy is blasting radio light. Our solar system, the atmosphere, it all creates a fog. Planck had to isolate that ancient whisper from all of that. Its instruments could detect temperature differences of a few millionths of a degree. The map it made is our most detailed baby picture of the universe. We're still learning from it. This whole journey, from a hiss in New Jersey to these maps from space, it's about curiosity. We built machines to listen back in time, to use engineering as a kind of archaeology, sifting through static to find signals from the past. And what these instruments show us isn't just a picture. It's a recipe. The first page of that recipe is elegant, and it's very strange. That map from Planck, it's not a photograph, it's a data set, a symphony of numbers turned into color. And to get the universe's story, we had to learn to listen to that music. The key was in the pattern. Those tiny temperature differences, they aren't just random static. They form a specific, repeating pattern across the sky. Hot and cold spots, like a complex fingerprint. Cosmologists don't just look at it, they translate it. They use a mathematical tool, a power spectrum. Think of it this way. If the sky map is a complex sound, the power spectrum is the musical score. It breaks the sound down into individual notes. It plots the size of the temperature fluctuations against their scale, how big each hot or cold patch appears, and that creates a graph with a very distinct shape. Peaks and valleys. This graph is the universe's barcode, and when we scan it, it tells us everything. The position and height of those peaks, they aren't arbitrary. They are direct echoes of physics from the infant universe. The first peak, the most prominent one, tells us something about the shape of space itself. Its position strongly indicates our universe is geometrically flat. Not flat like paper. Flat in the sense that parallel lines stay parallel. The angles of a triangle add up to 180 degrees. That was a monumental discovery. It means on the largest scales, the fabric of the cosmos isn't curved back on itself like a sphere. It isn't splayed open like a saddle. It is, for all intents and purposes, flat. And that flatness is a critical prediction of cosmic inflation. That explosive growth spurt in the first fraction of a second. Inflation would have stretched any initial curvature so dramatically that the observable universe appears flat to us. Just like a small patch of Earth looks flat when you stand on it. But the barcode tells us more. The relative heights of the peaks reveal the precise recipe of the cosmos. The second peak is connected to the density of ordinary matter. the atoms that make up stars and planets and us. The third peak gives us a measure of the dark matter, the invisible gravitational scaffolding that holds galaxies together. By reading this cosmic barcode, scientists can reconstruct the universe's composition with stunning precision. We now know ordinary atoms, everything we see and touch, constitutes less than 5% of the total cosmic budget. Dark matter makes up about 27%, and the remaining 68% or so is something even more mysterious: dark energy, the force driving the accelerated expansion of the universe. All of this, the shape, the contents, the history, it's encoded in the subtle hum of that ancient light. It's a single message sent when the universe was a newborn. And we are only now learning how to read it with perfect clarity. The cosmic canvas is flat, uniform, that presents a puzzle. How do regions of space, separated now by tens of billions of light years, share the same temperature? The same density? According to physics, they could never have been in contact. There hasn't been enough time since the beginning for light or heat to travel between them. Yet they match perfectly. It's like two people on opposite sides of the planet, never having met, wearing the exact same outfit. The universe achieved a coordination that should be impossible. This is where cosmic inflation provides an answer. It proposes that in the first tiny fraction of a second, far less than a trillionth of a trillionth, the universe underwent exponential expansion. Faster than light expansion, space itself stretched beyond comprehension. A region smaller than a single proton inflated to become larger than our observable universe. That solves the uniformity problem. Everything we see today was once crammed into an infinitesimally small, connected volume. It was all in thermal contact, sharing its temperature, before inflation blew it apart. That initial smoothness was stretched across the entire cosmos. But inflation did more than smooth things out. It also planted seeds for all future structure. In the seething quantum foam of the earliest universe, tiny energy fluctuations were inevitable. Particles flickering in and out of existence. These quantum jitters were microscopic. But inflation acted like a cosmic magnifying glass. It took those subatomic ripples and stretched them to astronomical sizes. The slightly denser patches became the gravitational seeds for galaxies. The slightly less dense patches became the great voids. The pattern of hot and cold spots we see in the cosmic microwave background is a direct, blown-up imprint of those quantum fluctuations. We are seeing quantum mechanics written across the sky. The theory makes another prediction. This violent stretching of space-time should have created ripples in the fabric of the cosmos. Gravitational waves from the birth of the universe. These primordial waves would have left a faint, twisting signature in the polarization of the ancient light. Scientists call this B-mode polarization. Finding it would be like discovering the fossilized footprints of inflation itself. It's considered the holy grail of cosmology. The search has driven teams to build telescopes in remote places, like the South Pole, where the air is dry and still, perfect for listening to this faintest of whispers. So far, a definitive detection remains elusive. The signal is incredibly faint, buried under noise from our galaxy's magnetic fields and dust. Each claim of discovery has been met with intense scrutiny. Often alternative explanations, the hunt continues. This connection is what makes the study compelling. It directly links the largest structures we see, the cosmic web of galaxies, to the smallest conceivable phenomena. Quantum fluctuations at the dawn of time. It bridges an almost unimaginable gap. The light we catch today is a messenger. It carries not just a picture of a 380,000-year-old universe, but the encoded echoes of its very first instance. To understand the full message, we have to look at what happened after that light was set free. How the universe transitioned from that smooth, hot plasma into the structured, star-filled cosmos we inhabit. That map we read like a barcode, it tells a story about what was there. But some of the most important characters in that story, they're invisible. They left their fingerprints on the light without ever touching it. The first is dark matter. It's a substance that doesn't emit light, doesn't absorb it, doesn't reflect it. It's ghostly, but it has mass. And in the early universe, its gravitational pull was immense. Ordinary matter, the hot plasma of protons and electrons, was being buffeted by the pressure of light. But dark matter was unaffected. It just sat there, creating gravitational wells. Pits in space-time, and the ordinary plasma, responding to both the push of radiation and the pull of dark matter. It began to slosh. It created sound waves. Massive, universe-scale acoustic oscillations. Think of a stone dropped into a still pond. The ripples spread out. In that primordial soup, these were pressure waves, racing through the hot plasma at over half the speed of light. They would compress, then rarefy, then compress again. And when the universe became transparent, when the light was set free, that sloshing stopped. It froze in place. The moment of release captured a snapshot of those waves. The compressed, hotter regions and the stretched, cooler ones. Those are the hot and cold spots in the cosmic microwave background. The precise spacing between them, the scale of those frozen ripples, that gives us the first peak in the power spectrum. It's a direct measurement of the universe's geometry. But the subsequent peaks, the second and third, their heights are dictated by a tug-of-war between ordinary matter and dark matter. Dark matter's relentless gravity suppressed certain oscillations. It changed the volume of that cosmic sound. By measuring the relative heights of these peaks, we can weigh the invisible. We learn that dark matter is not a minor component. It's the dominant gravitational architect. The unseen scaffolding the visible universe was built on. Then there is dark energy, an even more mysterious force. It doesn't clump like matter. It appears to be a property of space itself, causing the expansion of the universe to accelerate. Its influence came much later, long after the cosmic microwave background was emitted. But it still leaves a mark on the ancient light, through a subtle distortion. As the photons from the cosmic microwave background travel for over 13 billion years to reach us, their path is not perfectly straight. They pass by massive clusters of galaxies, by the great walls and filaments of the cosmic web. These are concentrations of both dark and ordinary matter. Their gravity bends the fabric of space-time, acting like a lens. This gravitational lensing very slightly warps the pattern of the ancient light. It smears the hot and cold spots, creating a faint, statistical swirl in their polarization. By measuring this subtle distortion, scientists can map the distribution of all the matter, seen and unseen, that lies between us and the dawn of time. It's as if the ancient light is a backlight, shining through the entire later universe. Any lumps in the cosmic fabric, any knots of gravity, they cast a faint shadow. A distortion we can decode. This allows us to trace the growth of structure across cosmic history, and measure the repulsive push of dark energy that began to dominate later on. So this light is more than a relic. It's a probe, a backlight that illuminates the invisible forces that have shaped everything. Its journey to us is a voyage through the evolving cosmos. A voyage that imprints upon it the story of all that came after its own birth. That light was set free, and it started the longest journey anything has ever made. For over 13.8 billion years, it's been streaming out. But the space it moves through isn't just sitting there, it's stretching, it's growing. And as space expands, it pulls on the light traveling through it. That's cosmological redshift. The waves of that ancient light get drawn out longer. Their energy drops, it cools down. What started as a brilliant flash of visible light gets redshifted all the way into the microwave band, a faint, cold whisper. That change is a direct record. The amount of stretching tells us exactly how much the universe has grown since the moment it was released. But the trip isn't just a straight line through empty darkness. The universe built structure over all those eons after the light left, and the light had to pass through all of it. Think of this ancient signal like a traveler. The road itself is stretching underneath it, and along that road, it encounters every landmark the universe ever built. It goes past massive clusters of galaxies. These are the biggest structures held together by gravity. Trillions of stars, huge oceans of dark matter. Their total mass is so huge it warps space-time around them. When the ancient light passes near, its path gets bent. That's gravitational lensing, like moving through a funhouse mirror made of gravity. Those slight deflections create tiny distortions in the pattern of the cosmic microwave background. They smear the hot and cold spots in a specific way. By studying those smears, you can map the distribution of all the matter, light and dark, that sits between us and the beginning. The ancient light becomes a backlight. It illuminates the cosmic web. There are later encounters, too. Some of these photons, on their way here, pass through enormous clouds of hot gas. Often in the vast spaces between galaxy clusters, the gas is so hot the electrons get stripped from their atoms. It creates a sea of free particles. When a microwave photon from the cosmic microwave background passes through this hot plasma, it can hit one of those fast-moving electrons. It gets a tiny boost of energy, a slight change in direction. That's the Sunyaev-Zeldovich effect, a late-time scattering, a final nudge given to the light long after its journey started. It adds another layer, another signal to pull apart. All these interactions, the smooth stretching of space, the gravitational tugs from dark matter, they aren't just noise. They're data. They turn the cosmic microwave background from a simple snapshot into a layered probe. By tracing this light's epic voyage, we're not just looking at the infant universe. We're doing a kind of cosmic tomography, using this primordial signal to scan the entire history of everything that formed after it. Every deflection, every subtle spectral shift. They're clues about what happened during those 13.8 billion years of darkness and light between its origin and us. And that sets a limit, a profound one. The light can only tell us about what it interacted with on its way here. It can't show us what lies beyond the horizon of its own journey. This ancient light forms a boundary, a horizon, the farthest edge of everything we can see. We call it the surface of last scattering. That's the wall of light where the cosmic microwave background comes from. A glowing spherical shell that completely surrounds us in space. It marks the moment, about 380,000 years after the beginning, when the universe first became transparent. And that's the ultimate limit. Because before that moment, the cosmos was an opaque fog. Light couldn't travel freely. Any signal, any photon from an earlier time would have been scattered, absorbed, and re-emitted immediately. It couldn't reach us in a straight line. So the light from the cosmic microwave background is the oldest messenger that can possibly get to our telescopes. It defines the observable universe. Everything we'll ever know about the cosmos through light comes from inside this bubble. A bubble whose wall is a baby picture, frozen in time. This horizon challenges our everyday intuition. We aren't at the center of this sphere. There is no center. Every observer, anywhere in the universe, would be surrounded by their own, identical shell of ancient light. If you could instantly travel to a galaxy 10 billion light-years away and look out, you'd see a cosmic microwave background, and it would form a sphere around you. The shell we see from Earth depicts not a place, but a time. A specific moment in cosmic history when the entire universe was at a certain temperature and density. So when we look out in any direction, we aren't looking toward an edge. We're looking backward to a common era. We're seeing the universe as it was everywhere at that infant age. That makes the cosmic microwave background a kind of cosmic fossil, but one that encases us. It's both a gift and a fundamental limit. A gift because it gives us a pristine snapshot of the early conditions, a detailed map we can study. A limit because it's an impassable curtain. We cannot see the universe before it was 380,000 years old with photons. The events of the very first instance, the moment of the Big Bang itself, the inflationary expansion, are hidden behind this glowing wall. We have to infer them from their echoes, like detectives listening for a faint sound from behind a closed door. This leads to a realization. The entire story of our cosmos, from the formation of the first atoms to the birth of galaxies to life on a pale blue dot, has all taken place inside this bubble. Within the observable horizon, yet the universe as a whole is almost certainly much, much larger than what we can see. Inflation suggests it's staggeringly vast, maybe infinite. What lies beyond our horizon? Other regions of space, forever disconnected from us, that underwent the same history but may have evolved differently. We can speculate, but we can never receive a signal from there. The light from those regions hasn't had time to reach us, and because of the accelerating expansion of space, it never will. So we're left with a profound cosmic solitude, defined by light. We're adrift in a vast ocean, but our view is confined to the inside of a single, magnificent bubble. A bubble whose walls are painted with the first light of creation. Everything we are and everything we know exists within its glow, that ancient light. It carries more than just heat. It carries a directionality, a kind of twist in its nature. That's polarization. Light as a wave, but vibrating in a specific plane. Like shaking a rope up and down or side to side. The cosmic microwave background has this faint polarization pattern across the sky. That's the next chapter. The next way to read it. And this polarization comes from two different sources. Each one tells a different part of the story. The first is E-mode polarization. It comes from the last scattering itself. Right before the fog lifted, the universe was a hot plasma, a sea of electrons. And when the last photons scattered off those electrons, the process imprinted a specific pattern. A curl-free pattern. The light carries a memory of that final interaction. Satellites like Planck have mapped this E-mode pattern with incredible precision. And it gives us an independent check on everything from the temperature map. The age of the universe, its geometry, what it's made of, the numbers match. It's like reading the same story in two different languages and finding the exact same plot. But the second type is the true frontier, the B-modes, a twisting, curling pattern in the light's orientation. Much, much fainter, and they could come from two places. One source is later, from gravitational lensing. As the ancient light's path is bent by all the matter it passes, its polarization gets twisted. That creates a lensing B-mode signal. We've detected that. It's another tool for mapping the cosmic web. But the other potential source is the Holy Grail. Primordial B-modes. A direct imprint of gravitational waves from the first fraction of a second. From the era of cosmic inflation. Think of that violent stretching of space-time not just as expansion, but as a quaking. A tremor, sending ripples through the fabric of reality. Those primordial gravitational waves would have twisted the polarization of the CMB as it formed, leaving a unique, swirling signature. Finding that would be like discovering fossilized footprints of the universe's birth pangs, direct evidence for inflation. And the strength of the signal would tell us the energy scale at which inflation happened, bringing us closer to the physics of the Big Bang itself. That hunt defines modern cosmology. It's a monumental technical challenge. The signal is incredibly faint, buried under noise from our own galaxy's dust and magnetic fields. So experiments have moved to the most extreme places. The high, dry plateaus of the Atacama Desert. The frigid, stable air at the South Pole. They build arrays of thousands of detectors, cooled to near absolute zero. Staring at the sky for years. Projects like the Simons Observatory. A new generation with unprecedented sensitivity. The goal is to read this one faint diary entry from the universe's first trillionth of a second. The philosophical weight is immense. We're trying to witness an event that's permanently hidden behind the curtain of the CMB, looking for the echo of a tremor that shaped everything. Using light as our only messenger, we build these exquisite instruments on a small planet, to listen for a whisper from the dawn of time, to understand how our entire cosmic home came to be. The constants we see in that ancient light, they aren't arbitrary. They're precise. The density of matter, the expansion rate, the balance of forces, they look fine-tuned. If the density had been just a tiny bit higher, everything would have collapsed long ago. If it had been a tiny bit lower, matter would have flown apart too fast. Galaxies would never have formed. Stars, planets, life, they rest on a razor's edge. That fine-tuning is one of the deepest mysteries in science. Why is the universe so hospitable? One answer comes from the math of cosmic inflation, and it's startling. It suggests our universe might not be unique. Inflation, that explosive stretching of space, may not have been a one-time event. It could be eternal, a process that creates not one universe but an endless, bubbling froth of them, a multiverse. In that vast ensemble, each bubble universe could cool differently. Each one could have its own random set of constants and laws. Most of these universes would be stillborn, too dense or too empty, too chaotic for any structure to form. But in a near-infinite sea of possibilities, a few bubbles, purely by chance, would have the right numbers, the right recipe for galaxies and stars and observers. And of course, we would find ourselves in one of those rare, habitable bubbles. Our existence selects for the conditions we see. That idea changes what the cosmic microwave background represents. In a multiverse, it's no longer the universal blueprint. It's not the one and only story of creation. It becomes a local artifact, a regional map of our particular cosmic neighborhood. The smoothness, the flatness, the specific pattern of seeds, all of that might just be the way things settled in our bubble. The ancient light is still a fossil, but a fossil from our backyard in a cosmos of unimaginable diversity. This shifts the philosophical ground. For centuries, we've sought a single, unique history of the universe, a definitive beginning. But if the multiverse idea is correct, there may be no single story. No unique beginning to speak of. Our entire observable cosmos, from the CMB to the most distant galaxy, could be just one episode, one part of an eternal, generative process with no ultimate start or finish. The question, why is the universe like this, might have a disarmingly simple answer. Because if it weren't, we wouldn't be here to ask. That transforms the CMB. It turns it from a simple snapshot into a portal. It pushes us to the frontier where physics meets philosophy. It asks us to consider narratives beyond our own. Could there be other cosmic bubbles where light travels at a different speed? Where gravity is repulsive? Where time flows backward? We will likely never receive a signal from them. They are forever beyond our cosmological horizon. But their potential existence forces a humbling perspective. The ancient light that has guided our understanding for decades now points to a reality far stranger and more vast. It urges us to look at that familiar map of the sky and wonder what other stories are written in light we cannot see. That cosmic map, the one that's so precise it still has these irregularities. These blemishes, they don't go away. The most famous one, they call it the axis of evil. It's not evil, it's just this alignment. On the largest scales, some of the hot and cold spots in the background radiation, they line up. They point in one direction. It's like the universe has a faint axis, a preferred direction, and that challenges something fundamental, the idea of isotropy. That the universe should look the same everywhere, no special direction, no up or down. The axis of evil suggests maybe there is one. Then there's the cold spot. A huge, cold region in the southern sky, much larger and colder than it should be. Like a bruise, it could be a random fluctuation, just a statistical fluke. But its size, it pushes probability. So there are other ideas. Maybe it's an imprint from a collision, another bubble universe, or maybe it's a shadow from a vast, empty void. A void billions of light years across that the ancient light passed through. These anomalies, they're like cracks, data points that don't fit. And for scientists, that's not a failure, that's the exciting part. There are three possibilities. First, they are illusions, effects from our own galaxy. Errors in the instruments. Every new telescope tries to see past that, to clean the lens. Second, they are real but just rare, statistical outliers. In a map of millions of pixels, a few strange patterns are bound to appear. We might just be the universe that got weird by chance. But the third possibility, that's the profound one. They could be real and meaningful, a sign of physics beyond our model. Maybe they're echoes from before inflation, a fossil from the very beginning, or maybe they hint at the shape of space, that it's not simply flat, that it's folded. Topology, like a screen that wraps around, investigating this isn't about disproving cosmology, it's stress-testing it. That ancient light, in its imperfection, keeps asking the hardest questions. It refuses to be a closed book. It's an open invitation, a puzzle, making sure the story is never really finished. That map of ancient light was a blueprint. But the universe wasn't a building yet. It was dark, quiet, for millions of years. The only architecture was those faint wrinkles, the slight overdensities frozen into the cosmic microwave background. Places where gravity had a tiny head start. Invisible dark matter was already clumping there, doing its patient work, creating deep, unseen gravitational wells. And ordinary matter. The hydrogen and helium gas from the Big Bang slowly responded. It was pulled in. For eons, nothing visible happened. The universe expanded and cooled in near total darkness. That was the cosmic dark age, a profound stillness stretching for hundreds of millions of years. But inside that stillness, inside those gravitational seeds, change was brewing. Gas collected, it grew denser, hotter. Eventually, in the hearts of the first protogalaxies, conditions became so extreme that a new process ignited. Nuclear fusion, the first stars were born. Astronomers call them population 3 stars. They were unlike any star we see today, made purely from the pristine hydrogen and helium of the early universe. No heavier elements, they were likely monsters, behemoths, hundreds of times more massive than our sun. They lived fast and died young, burning with a ferocious, ultraviolet brilliance. Their birth ended the Dark Age. Their light was the dawn of a new cosmic era. That intense ultraviolet radiation did something revolutionary. It began to tear apart the neutral hydrogen atoms that filled all of space, stripping electrons from their protons again. This process is called reionization. It fundamentally changed the nature of the cosmos. It made the universe transparent to certain wavelengths of light. It ended the epoch where neutral gas could absorb it. The fog was lifting for a second time, but now because of stars not cooling. This wasn't an instantaneous flash like recombination. It was a dawn that spread gradually. Bubbles of ionized gas grew around clusters of the first stars and galaxies, eventually overlapping to fill the cosmos. This great transition from darkness to light left its own subtle signature on the ancient light we study. The free electrons created during reionization could scatter the photons of the cosmic microwave background one last time. This late-time scattering imprinted a specific, large-scale pattern on the light's polarization. By measuring this effect in the CMB, scientists can pinpoint when reionization happened. Data tells us this cosmic renaissance was well underway when the universe was only a few 100 million years old. So the CMB carries not just a picture of its own release, but a faint echo of the first starlight that came after. This creates a breathtaking continuity. The microscopic quantum ripples stretched by inflation became the density seeds in the CMB. Those seeds, guided by dark matter, gathered the gas that formed the first stars. The light from those stars then reionized the universe, leaving a mark on the very same CMB photons. It's a single, unbroken chain, from the universe's first trillionth of a second, to its first 380,000 years, to its first billion years. The ancient light is the thread that ties it all together. It's both the starting point and the canvas upon which the next chapter was written. That ancient light isn't just a record. It's a laboratory, an experiment from the cosmos, frozen in time, run under conditions we can't recreate. Back in the universe's first moments, it was a particle accelerator, on a scale that makes anything we've built seem small. The energies were trillions of times beyond what our colliders can reach, and the cosmic microwave background is the readout from that experiment. By studying its patterns, we can test the laws of physics at their most extreme. Take neutrinos, these ghostly particles, they stream through us by the trillions every second. They're hard to detect, but they were crucial in the early universe. Their presence, their properties, they affected how the primordial plasma moved. And that movement left an imprint on the acoustic peaks in the CMB spectrum. So by analyzing that spectrum, cosmologists can count the number of neutrino species from the dawn of time. The data supports 3 light neutrino families, exactly 3, which matches what particle physics finds. So the CMB has weighed in on a subatomic question. It can also hunt for shadows, for things we've never seen. Exotic particles from theoretical models would have influenced the expansion rate. They would have shaped how structure grew in the infant cosmos. Their potential signatures are there, encoded in the subtle statistics of the CMB's temperature maps, its polarization. Scientists scour this data for any deviation from the standard model. A single, persistent anomaly could be the first hint of a new particle, a relic from the universe's first second. This search turns the sky into a detector for physics beyond our understanding. Even the constants of nature, their constancy isn't taken for granted. Could the strength of gravity have been different? Could the fine structure constant? 13.8 billion years ago, a variation would leave a fingerprint on the CMB. The precision of the Planck data lets us test this. So far, the evidence says these constants have been stable. To an astonishing degree over the age of the universe, this ancient light is a time capsule. It preserves the values of physics itself from an epoch before Earth existed. This laboratory also tests gravity. Einstein's general relativity has passed every local test, but does it hold across the cosmos, back to the earliest moments? The CMB is a proving ground. The way gravity sculpted the initial seeds, the way it lends the light on its journey, all of that is predicted by relativity. So we compare the story told by the CMB with the story told by the late-time universe, the clustering of millions of galaxies mapped in modern surveys. It's a consistency check. If the two stories disagree, it could mean a modification to gravity on cosmic scales, or a new, unknown force that acted only in the ancient past. Only on the largest structures, that changes the view of that faint microwave hum. It's not just a fossil to be admired, it's an active instrument, a cosmic accelerator whose results are still being analyzed. Every new, more sensitive map is like upgrading the detector in an experiment that began at the beginning of time. The practical application is profound. It's a direct line to understanding the most basic rules of our reality. By deciphering the data from this primordial lab, we're not just learning about where we came from. We're stress-testing the very framework of physics, using the universe's first light as our guide. We needed to hear something very faint, a whisper from the early universe. So we had to build new ears. The goal was to measure the cosmic microwave background, to pull its signal out of all the noise that pushed technology to its limits. And that effort left behind innovations, things we use now in everyday life. It starts with the detectors. That ancient light is faint and cold. To catch it, you need incredibly sensitive sensors. They developed things like transition edge sensors, kinetic inductance detectors. These are superconducting circuits. You cool them to almost absolute zero. At that temperature, they become tuned to the smallest energy, a single photon. The engineering behind these sensors made for cosmology found other uses. In medical imaging, similar superconducting tech is improving MRI machines, making scans clearer with less power. The same ideas are in advanced airport scanners. They can find subtler threats more accurately with less radiation. Even quantum computing uses these ultra-sensitive, cooled detectors to read the fragile states of qubits. The tools made to listen to the infant universe now help diagnose illness. They help with security. They help build new computers, but it's not only the hardware. The cosmic microwave background is a data problem. The signal is buried. Under our galaxy's glow, under dust, under satellite interference. To get the cosmic story from that noise, they needed new algorithms. They created new ways to separate signals, to clean maps, to analyze patterns on a sphere. These computational methods, born from cosmology, became contributions to machine learning. To big data science, the techniques for filtering cosmic static now enhance satellite imagery. They improve financial models. They help analyze genetic data. Trying to map the early universe taught us how to find meaning in huge, noisy datasets, a skill that defines our time, and then the missions, spacecraft like COBE, WMAP, and Planck. They were engineering marvels, built to operate in space away from Earth's warmth and atmosphere. Their development pushed cryogenics forward, the science of extreme cold, to keep instruments stable for years. It pushed precision optics and mirror fabrication to capture clean light. It refined satellite communication and pointing systems to incredible accuracy. The technologies perfected for these observatories ripple through aerospace, improving Earth observation satellites that monitor climate, improving deep space communication networks. This is a result of fundamental curiosity, the drive to answer a big question: where did we come from? It didn't happen in a vacuum. It forced us to build better tools, to think in new ways, to solve impossible technical problems, and those solutions circle back. They benefit society in tangible forms, sometimes life-saving forms. So the ancient light is more than a window to the past. It's a catalyst. Its faint signal from the edge of time still sparks innovation. The journey to understand our cosmic origins has a practical reward. Right here, looking for this light. It's a scientific search, really, but the meaning of it, that idea, it goes way past the lab. That first light, a kind of foundational glow where everything comes from, it's one of our oldest stories. Everywhere, across cultures, creation myths start with light breaking out of some original dark. In Egypt, the sun god Ra comes up from the waters of chaos, brings light, brings order. In Genesis, the first thing said is, "Let there be light." These aren't science, but they're deep human tries to get at the same mystery, the same one we're after now with satellites and math. The origin of everything, and the cosmic microwave background, it feels like a modern version of that. An evidence-based echo of that old intuition. We found our culture's creation story. Not written in words, but in microwaves. And that discovery, it sparked a new kind of art. Scientists take the temperature data from missions like Planck and make maps. Colors: reds for warmer spots, blues for cooler. But artists, they've taken that data and changed it. They see this ancient fingerprint as a kind of radiant mandala, a cosmic tapestry. They show it in swirling gold and deep blue, so the abstract map feels solid, feels sacred. That art bridges a gap. It turns the output from supercooled detectors into something that stirs you. Reminds you this data isn't just numbers, it's a portrait of our cosmic ancestry, like a family photo taken at the very dawn of time. Writers and filmmakers, they've woven this in too. The idea of a universal background radiation. This faint signal everywhere in space, it becomes a symbol. It can be a hidden connection linking everything. Or it can be imagined as a message, a deliberate imprint left by whatever made the universe. In stories, the CMB becomes the ultimate cold case, a clue from the first crime scene. It's a backdrop that adds depth, adds scale, a constant reminder to the characters, and to us, that our personal stories are nested inside an epic, one that started long before us. This back and forth between the scientific and the cultural, it matters. It fills out our imagination. Science gives us the facts, the breathtaking precision of the map. But art and literature and myth, they give us a language to feel its weight. They make the cosmic personal. When you see a beautiful visualization of the CMB, or you meet it in a story, it stops being just a physics topic. It becomes part of our shared heritage, a story that belongs to everyone. That might be its deepest impact. This ancient light gives a humbling view, a unifying one. It's a direct physical link to a moment before nations, before continents, before life. Every person, every creature, every mountain and ocean here, they're all bathed in this same fossil radiation. We are all, literally, made from star stuff that came together under the influence of those ancient temperature variations. The CMB reminds us of a shared origin, a common history written across the sky. In a world so focused on division, this scientific fact pushes a different kind of thought. It makes you consider our tiny, fragile place inside an immense and beautiful narrative. A story of light that started nearly 14 billion years ago, and it's still being told. The story in that ancient light is still being decoded. The next chapter needs new eyes. Sharper eyes than any we've built. The quest now is to see the faintest whispers inside the whisper, to find the subtlest patterns in polarization, the ones that might carry the signature of the universe's birth. That's driving a new generation of cosmic observatories. They're time machines with unprecedented sensitivity. High in the Chilean Andes, on a dry plateau called Cerro Toco, a monumental project is taking shape. The Simons Observatory, it's not a single telescope, it's an array, a symphony of instruments. Its core technology will be tens of thousands of superconducting detectors, all cooled to a fraction of a degree above absolute zero. This army of sensors will stare at the sky. It will map the cosmic microwave background's polarization with a detail we've never approached. Its goal is to hunt for the primordial B-mode signal. That twisting pattern could be the fossilized ripple of gravitational waves from inflation, but it will do so much more. By measuring polarization with this exquisite precision, it will also chart the distribution of dark matter across cosmic history, with finer resolution. It will weigh the neutrino, that ghostly particle, by seeing how its presence subtly suppressed the growth of the earliest structures. This one ground-based facility aims to transform our view of fundamental physics. Using the ancient sky as its laboratory, but Earth's atmosphere, even in the driest places, creates a veil. To see the cleanest signal, you have to go above it. That's the goal of proposed space missions like Lightbird, led by the Japanese Space Agency with NASA, a participation. This concept envisions a satellite orbiting a stable point 1 million miles from Earth. Its sole purpose would be to survey the entire sky in microwave frequencies, free from atmospheric interference. Lightbird would be exquisitely tuned to search for the large-scale B-mode polarization. It represents a dedicated, space-based attempt to answer the inflation question directly, to either find the definitive signal or place such stringent limits that we must reconsider our theories of the very beginning. Looking further ahead, cosmologists are already planning for a CMB Stage 4 experiment. This isn't a single instrument. It's a vision for a global effort on a grand scale. Imagine networks of telescopes, perhaps at both poles and in high deserts, working in unison, with millions of detectors scanning the sky for a decade or more. The data set would be staggering. It would let us move from a static map of the early universe to something closer to a film. We could trace how structures evolved with incredible detail. By using the CMB's lensing effect as a deep field probe, we could search for signatures of exotic particles that decayed in the first second, or even look for anomalies that hint at a cosmos before the Big Bang. These endeavors ensure that this ancient light will remain at the heart of discovery for decades. Each new level of sensitivity is like turning up the volume on a cosmic recording. We might hear the expected note of inflation's gravitational waves, or we might hear something completely unexpected, a sound the theory didn't predict. That is the true promise of these future time machines. They are built to test our best stories about creation, but they are also built to be surprised, to find the cracks in our understanding that will guide us to a deeper truth. The journey that began with a faint hiss in a New Jersey antenna is accelerating, pushing us toward the ultimate horizons of time and knowledge. That faint glow across the whole sky is a good teacher. It makes something you can't really picture into something you can. If you're trying to explain the story of the cosmos, this background radiation is a place to start. Because it's something we can measure, we can map it. It's not just a theory, it's evidence. It turns abstract ideas into something solid, like the expanding universe. You can talk about redshift, galaxies moving away, but it's a hard idea to grasp. With this background, you can point to its temperature. That chill, 2.7 degrees above absolute zero, that's a direct result of space stretching. Over billions of years, the light has been cooled by the expansion. It's a thermal record that makes the expansion feel real. It's not just a line on a graph. Then there are the early universe's sound waves. Explaining acoustic oscillations in plasma gets technical. But with this map, you can say, see these hot and cold spots. Those are the frozen crests and troughs of those sound waves. The universe rang like a bell, and this is the echo we caught. A fossilized vibration that turns a physics concept into something you can almost sense. You can almost hear that first note. Planetariums use this. They take the data from satellites like Planck and WMAP and put it on the dome. You sit back and watch the whole sky become that speckled map of the infant universe. It's a visceral thing. You're not just hearing about the Big Bang's afterglow, you're surrounded by it. You see the subtle variations that became galaxies. This builds a story. A presenter can start with this baby picture and walk forward through time. From quantum seeds to the first stars, to the cosmic web, to our own Milky Way. It shows the line of cause and effect. Across 14 billion years, this demystifies cosmology. It shows science isn't about wild guesses, it's detective work. We found a clue, a faint microwave signal, and from it, we reconstructed an epic history. That's a lesson in reasoning. It teaches how to ask questions of nature and decode the answers. For a student, it can be the spark. The moment they realize the universe has a history we can read, that they could help read it. It inspires not by saying, look how smart we are, but by saying, look what we can discover. This ancient light does more than illuminate our past. It lights a path. It invites everyone to look up and wonder what story the next whisper will tell. The meaning in this ancient light can get lost. There's a common idea that the cosmic microwave background is like a wall at the edge of space, that we're looking out and seeing a glowing border somewhere far away. But it's not that. It's an edge in time. In every direction, our vision just stops at the same moment, about 380,000 years after everything began. It's not a place you could ever reach. If you tried to travel toward it, you'd just find more universe. The glow would just be coming from a later moment, a closer moment in history. The wall surrounds us, but it's in the past. Another thing people often say is that we're seeing the Big Bang. We're not. We're not looking at the initial event. That's hidden behind the fog, the early plasma. What we see is the afterglow from when the universe became transparent. When the fog lifted, it's like trying to see the dawn. You can't see the exact instant the sun ignites, but you can see the first light that comes over the horizon and lights up the world. The CMB is that. The first cosmic sunrise captured. It's also different from other radiation. It's not the combined light from all the stars. It's not emission from our own galaxy. The Milky Way does produce microwaves, but the CMB is separate because of its thermal signature. Its spectrum is almost a perfect blackbody. That's the mark of something that was once in perfect thermal equilibrium. It's cooler, more uniform. It fills every bit of space in a way local sources don't. That all-pervading quality is a clue. It points to a primordial origin. Even the name can be confusing. We call it microwave background radiation because that's the wavelength we detect now, here. But that's not what it was when it started. It began as a searing flash, visible and infrared light. Over 13.8 billion years, the expansion of space stretched those light waves, lowered their energy, shifted them down into the microwave band. The label just describes its current state to our instruments, not what it originally was. Clearing this up isn't just about accuracy. It's about keeping the awe. If you think of it as a spatial edge, the story is about a place. If you see it as a temporal horizon, the story is about a shared origin in time. If you confuse it with the Big Bang itself, you miss the detective work of cosmology. And if you understand the stretched wavelength, you feel the expanding reality of the cosmos. Each clarification changes the narrative. It turns a simple glow into a connection to the dawn of everything. The fine-tuning in the light's data isn't a minor point. It's a staggering fact. The numbers from the cosmic microwave background, the density of matter, the size of those early fluctuations, they're balanced on a knife's edge. If the density had been just a fraction higher, gravity's pull would have been too strong. The universe would have collapsed back on itself long before any stars could form. And if the density had been just a fraction lower, matter would have flown apart too fast. It never would have gathered into the clouds that make galaxies. In either of those nearly identical universes, the story would have been brief. Barren, no planets, no chemistry, no life. The conditions for complexity for observers like us exist in an extraordinarily narrow window. And somehow, our universe landed right inside it. That observation brings us to a philosophical crossroads, the anthropic principle. In its simplest form, it says the universe we observe must be compatible with observers existing. We shouldn't be surprised to find ourselves in a universe that can produce us. It seems almost tautological, but the implications ripple outward. The CMB is the foundational data for this. It's the primary evidence that the cosmos isn't just any random arrangement. It's one tuned to allow structure, and ultimately, consciousness. This fine-tuning fuels deep debates about what it means. One interpretation looks for a deeper, undiscovered law of physics, a single, elegant theory that would inevitably produce these precise values. No room for chance. Another, more speculative idea is the multiverse. If an infinite number of universes exist, each with different random constants, then it's no surprise we find ourselves in one of the rare, habitable ones. Our existence simply selects for the conditions we see. In that view, the CMB isn't a universal blueprint. It's a local user manual for our particular cosmic neighborhood. For others, the exquisite balance points towards something beyond pure chance or necessity. It hints at a cosmos with purpose or design woven into its fabric from the first moment. These aren't scientific claims in the traditional sense. They're philosophical responses to the data. What the CMB does, unequivocally, is place humanity in a unique conversational position with the cosmos. We're not passive inhabitants. We're products of a chain of events so precise that our very ability to measure this ancient light and ponder its meaning feels like part of the story. The universe has produced a way to look back at itself, to question its own origins. The light asks us in its silent, mathematical language why the constants are just so. Why the stage was set so perfectly for the long drama of galaxies, stars, planets, and life. In seeking the answer, we're not just studying the cosmos. We're engaging in a dialogue with creation itself, trying to understand our place within a narrative that began with a whisper of light. The search for this ancient light breaks through traditional academic boundaries. It's one question that pulls in expertise from across the entire scientific landscape. Astrophysics gives you the cosmic stage, modeling how the universe expanded and evolved from a hot, dense plasma into the structured cosmos we see. Particle physics defines the actors, the protons, electrons, neutrinos, theoretical things like dark matter that filled that early stage. Thermodynamics describes the behavior of the radiation itself, that perfect blackbody glow we measure as a temperature. Each field offers a piece of the puzzle, but none can complete the picture alone. Then you get the deluge of data. A modern CMB experiment, like the Simons Observatory, doesn't produce a simple photograph. It generates a torrent of raw numbers, a cacophony of signals where the ancient whisper is buried under noise. Noise from our galaxy, the atmosphere, the instruments themselves. This is where data science and computer science become essential. Teams develop sophisticated algorithms to clean the maps, to separate the cosmic signal from the local interference. They use advanced statistics to analyze the patterns, testing millions of possible models against the data, to find the one that fits. The scale of the computation is immense. It pushes the limits of high-performance computing and machine learning. The goal is to extract meaning from what looks, at first glance, like random noise. None of this would be possible without engineering. The quest to hear that faint cosmic hum drives technological miracles. Engineers design cryogenic systems that cool detectors to a fraction of a degree above absolute zero. That's a necessity for sensing the CMB's subtle microwaves. They craft precision optics and mirrors to gather the cleanest possible light from the sky. They develop stable platforms and precise pointing systems for telescopes in some of Earth's most extreme environments: the high deserts of Chile, the frozen plateau of the South Pole. This convergence makes a CMB research project less like a single laboratory and more like a symphony orchestra. Astrophysicists, particle theorists, data scientists, statisticians, engineers. They all sit together, reading from the same cosmic score. They speak different technical languages, but they are united by a shared objective: to decode the message in that ancient light. This model shows how big science operates now. In the 21st century, the grandest questions about our origins can't be answered within the silo of a single discipline. They demand a synthesis. A fusion of deep theoretical knowledge with brute force computational power and breathtaking technical ingenuity. It shows that understanding where we come from isn't just about looking through a telescope. It's about building a new kind of collaborative intellect, one that can take a whisper from the edge of time and turn it into a story we can all understand. Decoding where the universe came from, it's more than just curiosity. It shifts how you see your own place in it. That perspective, built from ancient light, it brings a kind of quiet responsibility. When you really take in the timeline that nearly 14 billion years stretch from a hot, dense state to this fragile oasis, Earth, the planet looks different. It's singular, delicate, suspended in an immense ancient void, and knowing that everything we are, every element in our bodies, was forged in stars and scattered by cosmic events, that creates a sense of connection. Not just to each other, but to the cosmos itself. That viewpoint can drive an ethic of stewardship. If our planet is this rare, precious outcome of the grand narrative, then caring for its environment, its biodiversity, its future, that becomes a kind of cosmic imperative. It's the responsibility of the storyteller to tend to the story's latest, most fragile chapter. And the process of seeking this knowledge, it offers a model too. Mapping the cosmic microwave background, that's not one nation's work or one institution's. It's global. Scientists from dozens of countries collaborate on missions like Planck, the Simons Observatory. They share data, design instruments together, analyze results across continents. That cooperation, driven purely by the shared goal of understanding, it shows that humanity can unite around peaceful, monumental projects. It shows our intelligence, when focused beyond terrestrial conflicts, can achieve profound insights into our shared origins. That collaborative spirit is a hidden lesson inside the science, a blueprint for tackling other global challenges that need unified effort. With this grand narrative comes an ethical duty to communicate it clearly, honestly. In an age of misinformation, the story of the cosmos, grounded in evidence, refined through peer review, built by thousands, it has to be told with accuracy and accessibility. Making complex ideas like cosmic inflation or dark matter understandable, that's not just education. It's a defense against falsehoods. It lets people distinguish between rigorous discovery and speculative fiction. Fostering a scientifically informed society is crucial, because the choices we make about technology, our planet, our future, they're increasingly shaped by understanding how the natural world, on the grandest scale, actually works. In the end, the journey that starts with ancient light circles back to a human truth. Knowing we're made of stardust, that we're participants in a cosmic saga billions of years old, it can inspire a deep respect for the brief, vibrant phenomenon of life. It connects the vast to the intimate. This knowledge doesn't shrink our significance, it recontextualizes it. Our intelligence, our capacity for wonder, our ability to decode the universe, they become part of the story's unfolding. And with that comes a commitment to use our unique position in the cosmos not for division, but for understanding, to apply that hard-won cosmic perspective toward the betterment of our world and all who share it. The light from the beginning asks us to look outward and inward, and to act with the wisdom the universe itself has slowly, patiently revealed. That light from the beginning of the universe. It's not just an idea. It's physically here, right now. A little bit of the static on an old TV screen that was this same light. Those particles of light have been traveling for more than 13 billion years. And now they're moving through this room, through the air, through you. You are being touched by the afterglow of the Big Bang. It's not just a fact in a book. It's a personal connection, a physical link to the deepest past. It makes the story of the cosmos intimate. Immediate, it means the universe has a history, a continuous story, and we are inside that story. We are part of it. The calcium in your bones, the iron in your blood that was made inside stars, and those stars grew from the seeds in that ancient light. You're not just watching cosmic history, you are its current expression. A living chapter made from star stuff, reading its own origin. Thinking about this creates awe. It stretches the mind. It puts our daily worries, our personal struggles, against a backdrop of immense scale and beauty. That view brings humility. We are small on a tiny world, but it also brings a strange significance. The universe developed complexity that can understand itself. We are that process, becoming aware. This ancient light asks us to look beyond our immediate lives, to see ourselves as participants in a grand, evolving cosmos. The same laws that spin galaxies also govern your heartbeat. The same story of growth and change that shaped the cosmic web. It's echoed in our lives, in our societies. This perspective, from that faint whisper in the sky, that might be its real gift. It invites a moment of quiet wonder, a chance to step outside the everyday noise and feel connected to something eternal. It asks a simple question. If you are made of the universe, and the universe is within you, how does that change the way you walk through the world? That glow is a map of what we know and what we don't. It's the frontier of our understanding, a boundary written in microwaves. And for every answer it gives, it points to a deeper mystery. We know inflation happened, but we don't know what force powered it. Theorists talk about an inflattened field, a kind of cosmic engine, but its nature is entirely speculative. Is it a fundamental force we haven't found yet, or just a property of space-time itself? The ancient light tells us the engine was there. It doesn't tell us what fuel it burned. We see the signatures of dark matter and dark energy etched into the patterns. Their gravitational influence is clear, but we have no idea what they are. Dark matter could be undiscovered particles, or it could mean gravity works differently on cosmic scales. Dark energy might be a constant property of the vacuum. Or it could be a field that changes over time. The CMB gives us their weight in the cosmic budget. Their identity is still the greatest puzzle. Then there are the anomalies. The cold spot, the axis of evil, they could be statistical flukes in a huge data set. Or they could be genuine cracks in our model. Maybe they're imprints from a cosmos before our own. Or shadows of a complex space. These irregularities keep cosmologists awake, because they might be whispers of physics beyond the standard story. These questions push against an ultimate limit. The CMB is a wall of light. Behind it is the universe's first 380,000 years, a period of opacity we can't see through with photons. What happened in those first moments? What came before the inflationary burst, if anything? Was there a prior state, a different cosmos? Or does our idea of before just break down at that extreme? The ancient light marks the horizon of empirical science. We can theorize about those earliest instants. We may never get a direct signal from them, and that's the real gift of that primordial glow. It's not an end point. It's a starting line. It gave us a firm foundation, a detailed picture of the young universe. So now we can ask sharper questions. more profound ones. It reminds us that discovery isn't a journey toward final answers. It's an endless expansion of the questions themselves. The universe's greatest secrets might still be hidden in the faintest patterns of this radiation, waiting for the next generation of minds and machines to decode them. The quest doesn't end with this light. It truly begins with it. We end where we started. With a whisper, we followed that light from when it first broke free of a hot, dense fog, followed it on its 13.8 billion-year trip, right to the instruments we have now that can read it. This light is a time capsule. It holds the conditions of the very early universe. It's also a map. Its tiny temperature differences chart where galaxies would eventually form. And it's a lab, a place to test physics under conditions we can't make here. But more than anything, it's a story, how quantum ripples became the cosmic web, how darkness gave way to light, and how we made from stars, learned to read our own origin story in the sky. This light changed our place in the cosmos. It told us the universe is flat, that what we can see is finite, that most of it is dark matter and dark energy. It gave us a precise age, a detailed history. It connected the largest things, the cosmic web, to the smallest quantum jitters at the very beginning. Because of that, cosmology changed. It went from speculation to a precise historical science. We're not just wondering about the beginning anymore. We have its first photograph, its first data. So as we finish, there's one fact to hold on to. This ancient light isn't locked in the past. It's here, right now. It's a shared heritage, a physical link to the beginning that's all around us. Every person, every place on Earth, is bathed in this same fossil glow from the universe's first dawn. That's a gift of perspective, a reminder of our deep unity in this huge, ongoing story. Let that inspire a beginning, a new curiosity, a desire to keep looking up and asking. The universe's oldest stories aren't finished. They're still arriving, every day, in that faint microwave whisper. New telescopes, new minds will listen closer. They'll find answers we can't imagine yet, and mysteries we haven't even conceived. If this journey through time and light meant something, share that wonder. Subscribe for more trips into space's big mysteries. And next time you see the static on an old screen, or feel the quiet of a clear night, remember to look up. That first light is still traveling. Its story is still being told.